Back at it again. So remember, we are on chapter 17. We've been talking about sampling distributions, and today is going to be another one of those more theory-based days, and then the next lesson will cover more of like a specific example of how to use it. So we're actually still looking at sampling distributions. We have now covered a bunch of stuff to do with the sampling distribution of a proportion. But in this section, we're actually going to start looking at the other sampling distributions that are not proportions, all right? So we already talked about the whole normal curve, all that jazz with proportions, and we're going to use a lot of those same ideas for this lesson. The only difference is we're going to start talking about it in terms of when we're talking about quantitative data, all right? So let's go ahead and jump right into the slides, and we'll take a look at what we got here. So it says here, what about quantitative data? Now remember, what's the difference between quantitative and categorical? Quantitative is when you are receiving data that's actual measurements of something, whereas categorical was much more like our proportions of stuff, like we were saying what percent of people fell into what categories, all right? So it says proportions summarize categorical variables, like we just said. The normal sampling distribution model looks like it will be very useful because it's going to be used here as well. And it says, we can indeed use something like this. Even more remarkable, not only can we use all the same concepts, but it's almost the exact same model, which means we're going to be seeing a lot more of our normal curve. So, simulating the sampling distribution of a mean. Like any statistic computed from a random sample, a sample mean also has a sampling distribution. We can use a simulation to get a sense as to what the sampling distribution of a sample mean might look like. What is this saying? It's saying, hey, just like how if we went out and took a sample of a bunch of people, we would expect the proportion of them to not be the exact true proportion, but it could be anywhere near it, and it's going to be close to exact, and the further we get away, the lower the probability of that happening. It's saying you get the same thing here. If I were to go out and get a sample of all of your heights, the sample height should be close to the true height, but we would still expect it to be a full distribution because it would have some leeway to the left and right, depending on who is in our sample. It might be higher than the norm, might be shorter than the norm by just a little bit. And as we get further and further from the actual average height, our chances of getting a sample like that will get lower and lower. So it's saying we're still going to be using that same concept of the normal curve. It's saying that now, instead of having a proportion here, we're going to have an actual like mean of a situation. So in the case I just gave you, we talked about the mean height of a group of people. And again, as we get further away from that mean, the probability of things happening is going to get lower and lower and lower. All right, so that's what we got. So let's start. How would the average of something like this look? It says, let's start with a simulation of 10,000 tosses of a die. This is a six-sided normal die, all right? A histogram of the results is, notice, we would expect if you roll a die, the chances of getting a specific number is 1 out of 6, all right? And all of them have an equal chance of rolling. So notice all of these bars are kind of around the same height because each of them have the same chance of happening. Now, it's not a perfect one because this is an actual simulation, so we're actually rolling the dice. So we would not expect to get exactly, 1/6 of them to be the 1, 1/6 to be a 2, 1/6 of all the rolls to be a 3, and so forth, because that's just not going to happen in real world. All right, so you can see they didn't roll 2 quite as much as they should have. They rolled a lot of 4s, respectively. All right, so this is where it's going to slightly change. It says, now, what if instead of 1, we rolled 2 dice, all right, and then we averaged them together. So this is what they're doing here. They're going to take 2 dice, they're going to roll them onto the ground, all right, and when they pop up, let's say a 4 and a 6 roll up, they're going to then take that 4 and 6 and say, hey, what's the average of that? Well, the average of 4 and 6 is 5. So they would come down here and that would go into the 5 bar. All right. So they do this 10,000 times. They roll 2 dice, they average the 2 numbers together, they record what that average is. And they do this 10,000 times. And you can notice already it's starting to kind of look like a normal curve. It's a little too pointy to be a perfect normal curve. It looks a little bit more like a V, all right? But after rolling just two dice, so their sample size was two for each ones, and they did it 10,000 times, all right? So even with a small sample size of two, it's already starting to look like the normal curve. And why would it not be straight across like it was before? Well, in this case, you have to remember when you roll two dice, there's a lot more ways to roll a combined number, like adding these two together. They added the 10. That's actually pretty rare to get a 10, but there are a lot of ways to roll a 7. And what is the average of 7? Or sorry, what's 7 divided by 2 in this case to give you the average? 3.5. So that means that 3.5 would be your highest chance of being rolled, all right, because there's more ways to roll a 7 than any other combination like this, all right? Then it says over here, now instead of doing two, we're doing a sample size of three. So we're going to be rolling three dice, all right? And then they're going to add the three dice together, divide by three. That way they're getting their average again, so it's back to the same number. And they're going to do it again 10,000 times. And this is what their sampling distribution looks like. Notice as our sample size increased from two to three, we already are looking more like our normal curve than we were before, where we were much more V-like. Now we're getting more normal, all right? So let's see how normal this will start to look. You can see here they did a simulation now of also five dice. So now they've rolled five dice at a time, and then they add the five together, divide by five, and get their average and record it into this. And they do it 10,000 times, and it looks like this. So at this point, it is basically a normal curve. I mean, that's a pretty good normal curve. Now, remember, as we increase, so they go from 5 all the way up to 20 at a time over here, you'll notice what's the difference from this normal curve to this normal curve? Well, the bigger your n is, the closer your average of this will be to the mean, like the true mean. The higher your sample size, the closer you will be to the true mean of the population. All right. So that means, if you'll notice, a bunch of them are kind of grouped together right here in the middle between 3 and 4. Whereas before, look, here's between 3 and 4. A lot of them were between 3 and 4, but we also had like some guys out here by the 5. We still had some out here by 2. But you can see now by the 5 and the 2, it is completely empty. It's just not going to happen. When we've increased our sample size to 20, those options are pretty much gone. Our sample size is large enough that we are expecting all of our averages to be really close to that 3.5 mark. All right. So what is this telling us? It's telling us multiple things. Number one, this idea of getting this normal curve with the population mean in the middle is going to work the same for a sampling distribution for this type of situation, quantitative, as it did for our proportions. The second thing it's telling us is that as we increase our sample size, it seems like our whole sampling distribution is kind of getting squished into the middle, because more of our averages, we would have a higher chance of expecting them to be right on the true mean instead of being away. It goes back to that idea of the conversation we had in class where I said, hey, I told you guys I could flip a coin heads every time, and if I flip it once, would you believe me? And you guys all said no. And if I flip it a second time and I get heads again, would you believe me that I can always flip heads? And you guys are like, maybe. But once I do it 30 times, you're like, okay, we just watched him do it 30 times in a row. So either he can magically flip heads every time, or he's using some jacked up coin. All right. This kind of works like that. It's saying, hey, as our sample size gets larger and larger and larger, we would expect that average to get closer and closer to the real value of our situation. All right. So let's move right along here. So it says here, as the sample size, number of dice gets larger, each sample average is more likely to be closer to the population mean. We just talked about that. So we see the shape continue to tighten around the 3.5 because that's the true mean in this situation. All right. And it probably doesn't shock you to know that the sampling distribution of a mean becomes normal. In other words, the bell curve. All right. Now, this is going to come into a very, very big deal theorem that's not going to seem like a big deal, but just behind the scenes, it does a lot for the rest of this class in terms of what we'll be doing with stats. So it says the sampling distribution of any mean becomes more nearly normal as the sample size grows. All we need is for the observations to be independent and collected with randomization. We don't even care about the shape of the population distribution. This is the fundamental theorem of statistics, and it's also called the central limit theorem. I'm going to go ahead and do a full slide on what the book says the central limit theorem is in a second. But first, let's go ahead and look at some other fun facts about this. It says it should not be, or sorry, it is surprising and a bit weird, because not only does the histogram of the sample get closer and closer to the normal model, but this is true regardless of the shape of the population distribution. This means that if I were to, I don't know, talk about something like salaries for how much people make when they get out of high school. Well, if I look at a graph of that, here's a graph over here on the left-hand side. If I look at a graph of that, a lot of people when they get out of high school, all right, they're not making a whole lot of money, all right? There's just not many jobs that are hiring you straight out. So a lot of people will end up getting around this range of money. Now, there are some people that get lucky and jump right into a job that makes a higher amount of money, all right? And but it's just not going to be as much. So we're looking at a curve kind of like this, all right? And then there's those people that, they're maybe their parents already own a businesses or something, and they're just making a ton of money right off the bat. Now there's not going to be as many of those, but there's probably still some. So it's saying that, hey, look, this would be not normal. It is super, super, super skewed, right? Because most of the people would be making not much money starting off. And then as the amount of money increases, there's just not as many people that would do that straight out of high school. Okay. So this does not appear to be normal, but it's saying that the mean of this situation, so what's the average salary you would expect to make out of high school? It says that the mean of that situation is normal when we're looking at the sampling distribution. So what does that mean? It means that, let's say, in this whole population of all people that graduate from high school and go, you're talking millions of people, all right? If I go out and find, I don't know, 500 people and find the mean salary of those 500 people, we would expect that mean to be pretty close to the actual mean of all people that go out and get jobs after high school. All right. We would expect the mean of our sample of 500 to be pretty close. Now, we would know that it would end up being off a little bit to left and right, but in general, that's what creates our sampling distribution. And again, we now know that it will take a normal curve. So the sampling distribution will be normal for when we're talking about the mean, even if the original data about what we're talking about is not the normal curve. So that's what it's talking about here, that it's true regardless of the shape of the population distribution. It's saying no matter the crazy situation or the graph it creates, the sampling distribution will always be a normal curve. All right. So it says the CLT works better and faster the closer the population model is normal itself. So it's saying, like, okay, this is crazy, but eventually, as the sample size gets bigger and bigger, the sampling distribution turns into this normal curve. But down here, it's saying if your original information, like when we were talking about the heights of people, is already normal, then the new one's going to be super, super normal. All right. So let's go ahead and look at what your actual central limit theorem is in the textbook. In the textbook, it's going to say that the central limit theorem is the mean of a random sample is a random variable whose sampling distribution can be approximated by a normal model. The larger the sample, the better the approximation will be. All right, so what does that mean? The mean of a random sample is a random variable. It means that anytime you go out and get a sample, it's going to have a different average every time. So we're going to refer to it as a random variable because it won't always be the same. But what we do know about it is that it will always be in a normal curve or the normal model, all right? It also says that the larger the sample, the better the approximation will be. So that means that the more people you have in each sample that you're drawing, the closer it will be to a beautiful, perfect normal curve. All right. So this is extremely powerful. Why is it so powerful? Because we've been dealing a lot with probabilities. In the beginning of this, in the last few lessons we just did, we were able to look at certain situations where we drew a sample and we were able to tell the probability of getting that sample by using the normal model for this. Now, notice when we used our normal CDF or when we used z-scores or all of that stuff, all of that stuff is only possible on the normal curve. We can't do a normal CDF question in our calculator if we don't have a normal curve to begin with. If it's skewed right, like that salary question I was just talking about, we wouldn't be able to use the normal CDF in our calculator. So what does this mean for us? It means that now we have a powerful tool that takes any situation and turns it into our normal curve. All right. And then once it turns it into the normal curve, we're going to be able to do all of our powerful statistics with it. All right. Now, tomorrow, we're going to look at, well, not necessarily tomorrow, whenever you're watching the next video, we're going to jump into two other things. One, just like with the proportions, there is a bunch of conditions that we want to make sure we fulfill before we do these. And number two, we will do an example problem of using this material. So again, because this was just a lot of theory today, I'm not going to give you any work on it, but do expect to see another video drop on this chapter that's going to. So naturally, the sound cut out at this point of the video, and I'm not recording the whole thing. So, have a wonderful day, and as always, guys, stay fit, stay healthy, and have a wonderful week.